Okay, here we go, kiddos. This is the Unit 7. This is the test that I provided to you as an example. So a lot of these questions are parallel. There might be some slight differences here and there, but again, I can't answer every question for you. You have to do some of it. This is just a good example, and hopefully it will kind of lead you down maybe a path that will get an answer for you on the actual test itself. All right, let's go ahead and start working. Okay, here we're looking for areas. So that's going to be integrals. Okay, so an area in the first quadrant bounded by these things. Okay, so we have y is equal to x squared. And then we have this, which is ultimately y is equal to x plus 2. So x plus 2 looks something like that. All right, so we are looking to find this area right here. What I notice is I'm probably going to integrate up and down, so that's going to be the dx style. Now, what I need to know before I do this is where does my integral start and stop? So in essence, what I need to first figure out is where is x squared equal to that x plus 2? So where is y equal to 1? All right, so a little bit of mathematical wizardry here. We see what x plus 1 minus 2. All right, so we are going to have to integrate from -1 to +2. Okay, so now we're ready to go. All we're doing is finding this area, and so it'll be the top minus the bottom. So this area is going to be the integral from -1 to 2 of the top, which is the line, which is that x plus 2. Again, what I'm looking at is this is y is equal to x plus 2. Minus the bottom, which is x squared. All right, let's do one slight cleanup step here. All right. So again, after the initial setup, it should be kind of easy peasy. Yeah, it's just the top minus the bottom, know where the integral starts and stops. All right, so I think this is a swoopy swoop kind of a graph. So this is 1 divided by the square root of x minus 1. So vertical asymptote at +1 on this guy. Okay, no negative portion of this. That makes sense. So this is +1. And this graph comes down like this. And this is being integrated from +2 to +5. So this is pretty straightforward. I'm going to integrate up and down, which is again a dx kind of method. And this is going from 2 to 5. This should be pretty straight away, unless barring some confusing math that might exist. I'm not exactly sure, but some confusing math might exist. Let's see here. So this area is going to be the integral of 2 to 5 of x minus 1 to the negative 1/2. Okay, so this is an embedded function. This is probably going to be a u substitution. But u substitution was chapters ago. That's not that bad. Okay, so u in this situation is going to be x minus 1. That makes du equal to dx, 1 dx. That's fine. It's perfect. I do have to reevaluate my limits. So 5 is now 4. 2 is now 1. And then because I'm going to this u, I'm not going to go back to the x upon my solving of this integral. I'm not going to go back to x because I reevaluated my limits of my integration. If I left 5, 5, and 2, 2, then I have to go back to x. All right, so this now is from 1 to 4 of u to the negative 1/2 du. Okay, I can absolutely integrate this. So this is 1/2 times 2 from 1 to 4. And so this is a square root. So this is going to be the square root of 4 minus the square root of 1. Okay, here we have a volume being rotated, rotation. So this is a rotation. So a disk or shell method. So let's take a look. We got 3x minus x squared. I. Okay, so this is part of the region. Let's see what the boundaries there are. Find the volume of the solid formed when is bounded by that, and y is equal to 0. Y is equal to 0 is the x-axis. So this is the boundary right here. Okay, this is the boundary. I do need to know where this integration starts and stops. Again, let me explain myself a little bit. I'm going to integrate up and down, which is a dx method. So I need to know where this integration starts and stops. And so that is where 3x minus x squared is equal to 0. So that means x squared minus 3x is equal to 0. So that's going to be at 0 and positive 3. Not a major part of the problem, but it's definitely necessary. All right, so let's squish that down a little bit more. All right, so this is at 0 and 3. Okay, we are rotating about the y-axis. So this is a dy method. So these things do not match up. So this is going to be the disk method, which is again the pi r squared or r squared minus r squared kind of method, whatever the case may be. This one, there is no little radius, so it's just a big R squared dx. So this is the method that we're going to use, the pi r squared method. All right, so here we go. Volume is equal to pi integral from 0 to 3 of 3x minus x squared, that's the r squared dx. All right, so this is what? X to the 4th minus 6x to the 3rd plus 9x squared. see what we get. All right, the area of the region is revolved about, well, x is equal to 5. What is the volume? Okay, so again, volume. So let's see what we have here. We have x squared. We have 4x, which is going to cut into that. Let me make this a little bit more drastic. See what we're doing here. All right, so we have this not enough. And we have 4x, which looks something like that. Again, this is a little drastic. And x squared is equal to 4x at 0 and 4, and that is in the x. Yeah, 16 is equal to 16, makes sense. So again, I'm integrating up and down. This is a dx method. My integration starts at 0 and goes to 4. As such, okay, let's take a look at how this is being revolved. So this is being revolved around x is equal to 5. So x is equal to 5 is out here, which is a dy kind of revolution. These do not match up. So this is going to be the pi. Did I make a mistake before? Give me 1 second. I did make a mistake. Oh, wow. I made a huge mistake. Made a huge mistake. Wow, okay. Is that the only one that I made? It is the only revolution. Yeah, so I was right off that wrong. Gosh darn it. Okay. I'm going to come back to number 3. Number 3 is incorrect. I used the wrong method. I don't know why. Man, okay. So because these things don't match up, I have to use the shell method, which again is like the x and then the function kind of method right here. This is the kind of method that I have to use. I made a mistake and I needed to use this method on, wait, I'm sorry, that was 2 pi. And then here's where I adjust my my axes. Sorry about that. Here we go. Gosh, I can't believe I made that blatant of a mistake earlier. Sorry about that. Here we go. Let's get back into it. So let's set this up properly. So this volume is going to be equal to 2 pi, the integral from 0 to 4. This is, again, x. I'll leave it blank for right now. And this is the top minus the bottom. So this is 4x minus x squared dx. All right. Now, because this is moved, I have an option. I can go x minus 5 or 5 minus x. Again, I need to ensure that this number is positive, and if x is a number between 0 and 4, this is the method that I can ensure that it's going to be positive. So this is going to be the 5 minus x. All right. Let's do some math here. I'll go with 5. So this is 20x minus 5x squared. And then the x, which is going to be negative 4x squared plus x to the third. So this is going to be x to the third minus 9x squared plus 20x. All right, so 64 pi is what I got on that one right there. All right, I do apologize about number 3. Let's go back and handle this business properly. Let's right some wrongs. Okay, so all of the base information is correct. All of that base information is right. However, the method that I used was incorrect. Okay, because these things don't match, I have to use the 2 pi integral x f of x kind of method, right? Or y dy. But in this case, I'm integrating up and down, so yes, it is dx. All right, so here we go. So this volume is going to be 2 pi integral from 0 to 3 of the top minus the bottom, which is the parabola. So this is going to be x. The axes isn't moved, and this is going to be 3x minus x squared dx. All right, so this is negative x to the third plus 3x squared. There you go. That is now correct. I'm sorry about that earlier. Just set it up with the wrong method. All right, so here we have a derivative. Okay, so let's remind ourselves what the heck the derivative of a inverse cosine is. So an inverse cosine is 1 minus u squared negative 1 with a u prime. Okay, that's what our base derivative is right there. Oh my gosh. All right, so let's just stash that there for right now. let's identify some stuff. So u in this case is 3x. So that means u prime is 3 and u squared is 9x squared. All right, so this derivative ultimately is going to be equal to 1 minus u squared, square rooted all underneath -1 u prime, so that's going to be all under -3. Easy peasy lemon squeezy. Okay, again, this is asking for a derivative. So let's go ahead and remind ourselves what the heck a derivative of the inverse secant is. Okay, so this is what the derivative is. So let's go ahead and identify some stuff. So u is 1/2 x squared. So that means u prime is x, and u squared is 1/4 x to the 4th. I'll probably have to factor out some stuff here. Do some math. All right, so here we go. So this derivative is u square root of u squared minus 1 underneath u prime Right, so first thing that I'm going to address, I'm going to take out a 1/4 of this. So this is going to be x to the 4th minus 4. The square root of 1/4 is 1/2. Okay, so that's what that is. Let's go ahead and just jot that down right here. So this is going to be, in essence, 1/4, because 1/2 and 1/2 is 1/4. X squared, x to the 4 minus 4, underneath x. Okay, still stuff to do. The obvious one is to cancel off this x with one of those denominator x's, and then multiply by this reciprocal, which would, in essence, put a 4 to the top. Let's take a look. Looks like answer D to me. All right, integral time. All right, so what I see is an integral of a squared minus u squared du. And so if that is true, this is going to be the inverse sine of u over a plus c. Okay, so let's see what we have, see if we have to do any tricks. It really doesn't look like it, but who knows? Let's see. So during my initial substitution, I made my a squared equal to 4, so that makes a equal to 2. I made my u squared equal to y squared, that makes u equal to y, and du equal to dy, and that's perfect. That's exactly what we want. We don't have any extra pieces. There's no limits to reevaluate, so that means my answer is going to involve y's when all said and done. Okay, so here we go. I don't think there's anything holding us back from victory on this one. So this is ultimately going to be equal to Actually, let's just do the substitution just to make sure I did everything correctly. So 4 is a squared. Y squared is u squared. dy is du. So yes, I did do all of this stuff correctly. So this is going to be inverse sine of u over a plus c. All right, here, this one kind of looks like an integral of u squared minus a squared du. And if that's true, this is going to be 1 over a inverse secant of u over a plus c. All right, let's go see if we can make this happen. All right, so a squared I said is 1. That makes a equal to 1. Good to go. U squared I said is 4x squared. That makes u is equal to 2x. I'm going to have to figure this out. That does need to be solved. And du is equal to 2 dx. And again, that also needs to be solved just to make sure we don't have any extra pieces. I don't think we do, but again, let's let the math worry about it. Okay, so one thing that I need to do is solve for dx, and that's going to be equal to 1/2 du. Another thing that I'm going to have to do is I'm going to have to solve for x, and again, that's going to be 1/2 u. Okay, there's no limits to worry about, so my answers are going to go back to an x when all said and done. Okay, making the substitutions into the original equation. So x is 1/2 u, square root 4x squared is u squared minus 1, which was a squared, times dx, or dx is on top, you could look at it that way as well, and which is 1/2 du. All right, hooray. The 1/2 eliminates the 1/2, setting up my equation perfectly with no extra pieces. This is exactly what I wanted. This is awesome. All right, so let's go ahead and actually take this integration. I don't have to do any other mathematical wizardry to make this happen. All right, so this is going to be equal to 1 over a, which is 1, so 1 over 1. Inverse secant of u over a, which is 1, plus c. All right, be conscientious of this 4x. Hopefully part of that gets eliminated, which I'm pretty sure it will, but let's just take a look. So I see this as the integral of a squared minus u squared du. And if that's correct, this is going to be the inverse sine of u over a plus c. Again, not a plus c because this is a definite integral, but all right, let's go ahead and see what we have here. So a squared, I said, is 4, thus a is equal to 2. U squared is equal to x to the 4th. That makes u equal to x squared. That makes du equal to 2x dx. All right, so here I'm going to do my trick of solving for dx. I don't know if it's so much of a trick, but that's what I'm going to do. So that goes to 1 over 2x. So that's really good. So I'll have a leftover 2, but that's not a big deal. Another thing that I'm going to have to do is reevaluate my limit. So 1 going in for x, 1 squared is still 1. 0 going in for x, 0 squared is still 0. Okay, so I have this reevaluated. And so that means this, like I'll go back to my previous example. Because this is a definite integral and I make substitutions for these, this u, when I actually do my integration and I turn it into this statement right here, I'm not going to turn this back into an x. It's going to literally stay the letter u. Don't resubstitute in an x back into it. Okay, so here we go. Let's make some basic substitutions. Back to the original function. All right, so this is the integral from 0 to 1. 4x, I'm not sure about just yet. Hopefully, I'm able to do something with that. 4x, and this is a squared minus u squared. And dx is 1 over 2x du. Hooray. So what I see is the x gets eliminated, and 2 simplifies this 4 to a 2. So I'm able to take out this 2, but I'm able to do this integration. So this is going to be 2, and this, as I said, is going to be the inverse sine of u over a. So that's u over 2. And this is being evaluated from 0 to 1. Okay, so 2 basic math problems here. One is when I put in the 1, and the other one is when I put in the 0. So the first, in essence, is when is the inverse sine of 1/2? So that makes sine equal to 1/2. Sine is a y coordinate, so where is the y really, really small? At pi over 6. Is where the y coordinate is really, really small. Okay, the other one is the inverse sine of 0. So that makes the sine of my angle equal to 0. So where is the y coordinate equal to 0 for angle? It's right there. That's where the y coordinate is equal to 0. And that is 0. Okay, so this is 2 pi over 6 minus 0, and so this is pi over 3. Okay, and getting down to it now. Ooh, particle motion. Back in the Dizzy kind of problems. All right. Oh, total distance. All right. Okay, total distance. Okay, this will get you the net change, and then you have to get the absolute value to get a total distance. So you have to take the absolute value of velocity to get you this total distance. It's the integration of a rate. All right. So what does that mean? So it's all fine and dandy to say, or it's all fine and dandy if you have a calculator. And I'm kind of pretending like we don't. And so what I want to know is, when is this velocity equal to 0? Because if my velocity does something like this, and I'm supposed to integrate across, like, from 0 to 3 or something like that, like I'm supposed to do here, if I have a negative velocity, that is going to take away distance. So I need to find where is this negative velocities, and then make that negative area positive. So I need to know where are these velocities equal to 0 so I can make those distinctions. All right, so velocity, here we go. Let's factor out a free t. So this occurs at 0 and positive 2. All right, well, 2 is in our domain of 0 to 3, so let's go ahead and take a look at this. All right, so if I plug in a number like 1, this is going to get a negative answer. And if I plug in a bigger number, it's going to be a positive answer. So if I need to accomplish this absolute value of velocity, what I'm going to do is I'm going to have to break this up into two integrals. One is the integral from 0 to 2, and the other one is the integral from 2 to 3. Now, because I'm going to get a negative answer in that part right there, and again, I know that because my velocity is negative. So if I integrate my velocity is physically negative in that part. So what I need to do is turn this answer, which is going to be negative, positive. And so how I do that is pretty simplistic. I just chuck on a negative sign in front of that, and now that negative answer is going to be seen as a positive number. All right, so the integral of velocity, I'll just kind of work on the fly, is going to be t to the third minus 3t squared. T to the third minus 3t squared. All right, so that first one, I'm plugging in a 2. So as I said, this is coming out to a negative answer. This would be a negative answer if I didn't counteract it. So negative, negative, positive 4 plus 4. Okay, set up the integral. Do not evaluate the volume that is rotated. Okay, so let's take a look at our picture. Let's understand what the heck is going on here. So we have a y squared, which is a sideways parabola, and the x is equal to 2y. I don't understand what that is. Y is equal to 1/2 x. Okay, so y is equal to 1/2 x. With something like that. All right, again, this is this, and just straight up looking at the equations, it's probably best to integrate this way, which is in the dy style. So this is going to be 0, and that upper boundary is where y squared is equal to 2y, so this is what, positive 2. All right, so that is my initial setup. Let's see how these rotations take place, and hopefully I won't make another mistake. All right, so in question A, let's group this up. In question A, they want me to rotate it about the x-axis. All right, so this is a dx style. These do not match up, so that means I need to do the 2 pi y f of y dy kind of method right there. That's what I need to do. Because they don't match, I need to do the shell method. All right, so this is a dx kind of method. All right, so, but I need to integrate dy, so they don't match. So my volume is going to be equal to 2 pi integral from 0 to 2 of y, and this is the big, which is the line, so this is 2y minus the parabola y squared. This is the right minus the left. So again, you have to kind of think of like the area. This thing is kind of representative of an area. So it's the right minus the left. So this is what, 2 pi integral 0 to 2 of negative y to the third plus 2y squared. I don't know if you have to take that last step there, but that's what you can do. Long story short, it's right. Again, they don't tell you to integrate it. They don't tell you to get an answer, so don't. Okay, this next problem is asking us to integrate about the y-axis, which is a dy method. And so these things do match up. So this is going to be the pi big R minus little r squareds kind of method. This is called the disk method. So again, the big R from my radius for my axes is the red line, and the little radius is the blue line. All right, so this is going to be the line, which is 2y, so big radius squared minus little radius squared dy. Long story short, this is correct. So this is what, 4y squared minus y to the fourth. That's good enough. Just leave it like that. Okay, at first quadrant, find the region, find the area, okay? Find that area. So y is equal to the square root of x divided by 2. Let's take a look at that. Okay, so it's just a square root. It just doesn't go up as quickly. It's still a square root. First quadrant, 1 to 4. Okay, so integrating this way, this is a dx method. I don't really see any hang-ups here. Maybe it's hard to integrate or something like that. We'll see. All right, so this area is going to be the integral from 1 to 4 of 1/2 square root x, or x to the 1/2. I'm going to obviously take out this 1/2 right here and just worry about the x to the 1/2, but okay. So this is x to the 3 over 2, 2/3. 1/2 that is already out there, and this is going from 1 to 4. Okay, so here 2 is eliminated, so this is an outside 1/3. 4, square root 4 is 2, 2 to the third is 8. Minus 1, square root of 1 is 1, 1 to the third is 1. All right, so that's the area. Oh, I see what they're trying to get at. All right, so now find a value of k that divides the region into 2 equal areas. All right, so there is a k somewhere in between this 1 and 4 that this area is going to be split in half. So this area, if I split this in half, is going to be 7/6. Okay, that's what the half of the area is. And so I'm going to integrate from 1 to k, and I'm going to make sure that is equal to 7/3. All right, so the area that they speak of in this case is going to be an integral from 1 to k of the same gosh darn thing, but I know that the answer is going to be 7/6. All right, so long story short, this is 1/3 x to the 3/2 from 1 to k, and that's going to be equal to 7/6. All right, this is k to the 3/2 minus 1 to the 3/, which is 1/3, and this is equal to 7/6. All right, so the first thing I'm going to do is I'm going to multiply by 3. So that's going to leave me with k to the 3/2 minus 1 is equal to 7/2. I'm going to add 1. So k to the 3/2 is going to be equal to 9/2. And then I need to square this and cube root this. So k is going to be equal to 9/2 to the 2/3, whatever that is. I'm not really that interested in. But it should be a number between 1 and 4 if I've done everything correctly. It should be a number between 1 and 4. So let's just check it out. Yeah. Oops. I don't know why I get 3/2. It's 9/2. Yeah, that number makes a lot more sense. There it is. So 9/2 to the 2/3. That's that value of k. Find the solid of the base of the region whose cross sections are cut perpendicular to the x-axis, so that means dx, are isosceles right triangles with one leg in the r. All right, so what this is describing is this. So we have this graph, and it goes again from 1 to 4. And what we're going to do is we're going to build isosceles right triangles with one of the legs in there. So this is the length across. Okay. So in case you still have a difficult time seeing what the heck we're doing, this is what we're doing. Okay, so that length across is just the y coordinate. So this is going to be 1/2 square root x. All right, that's what that equation is, right? 1/2 square root x, yeah. All right, so that's the length across any particular part. All right, now, to figure out this volume, the volume is going to be the integral of the areas at every single point. Okay, so I need to figure out what are these areas with a length of 1/2 square root x. So the shape that we're building on top of this thing is isosceles right triangles with the base as L. So this implies that the area of this is 1/2 base times height, aka 1/2 L squared. So plugging in the L, this is 1/2 of 1/2 square root x squared. So 1/2 squared is 1/4, so this is going to be 1/8, and then the square root of x squared is x. So the area is ultimately 1/8 x. So that means my volume of this is going to be the integral from 1 to 4 of 1/8 x dx. Obviously going to take out this 1/8, but it's a simple integral now.